Einstein said that no object can travel faster than the speed of light. But you don't have to take his word for it. Do the experiment. Put an electron through a potential difference and it'll come out the other end faster. But can it go faster than the speed of light? In this problem, we'll use the relativistic form of the momentum to see what Einstein's theory of relativity predicts for an electron accelerated through a potential difference to high speeds, and compare with the classical prediction. Let's see the problem. An electron moves along a straight line in a uniform electric field E with speed v, where the electric field is along the electron's direction of motion. The electron starts from rest at x equals t equals 0. Classically, what is its speed after a time t has elapsed? Relativistically, what is the electron's speed after a time t? Now consider an electric field 10 to the 7 volts per meter, and find the speed of an electron which is accelerated from rest for a time period of just 0.1 nanoseconds and 0.2 nanoseconds in a linear accelerator. Let's say the electron's motion and the electric field are along the x-axis. Then the electron experiences a force given by force equals the charge of the electron times the electric field due to the electric field, where recall that the charge of an electron is equal to minus e, where we take e equals 1.6 times 10 to the minus 19 coulombs. I've given that number in the solutions. Now, Newton's second law says that force equals mass times acceleration. So we set the force due to the electric field equal to the mass times the acceleration, which is dv dt. And then combining these two equations, we can solve for the magnitude of the acceleration of the electron due to this electric field classically. So we'll get that the acceleration a, which is just the magnitude of dv dt, equals the magnitude of the electric field times the charge E over m. Good. So if the electron starts from rest at time t equals 0, then we know that when we integrate to get the velocity, recall the velocity is the integral of the acceleration with respect to time, then the bounds of the integration are from 0 to t, if we start at t equals 0. So integrating, we'll find that the velocity of the electron as a function of time, classically, is given by e over mt, since of course integrating a constant acceleration with respect to time is just going to give us a factor of time. So these are just the magnitudes I've written here, but of course we can see with this minus sign up here that the electron's motion will actually be in the negative x direction, opposite the direction of the electric field. But here we've just written the magnitude. So as we put as input at t equals 0, the velocity of the electron equals 0. But as t gets large, so at large times, the velocity of the electron also gets proportionally large. So what this looks like is a straight line on a plot of the velocity versus time, whose slope is the charge times the field over the mass of the electron. So importantly, at some time, because this is not bounded in any way, the electron's velocity will actually be faster than the speed of light, according to this classical prediction. So if this is the speed of light, then at some time, we would classically predict that the electron will reach a velocity faster than the speed of light. Now, what would we expect relativistically? Relativistically, we'll use the relativistic form for the momentum, P equals gamma mv, where gamma equals 1 over root 1 minus v squared over c squared, and derive the relativistic form of Newton's second law. So rather than F equals ma, we need to figure out what the relativistic version is. And we'll do that by taking F equals dp dt, which you know classically, but here we're going to use the relativistic form of this momentum. And here we're only concerned with the magnitude of the force and the magnitude of the ultimate velocity. And because our force is along the direction of the motion, of the velocity, it's okay to just use the magnitudes here and forget about the vectors. It would be more complicated if the force wasn't along the direction of motion. So plugging in, we're taking the time derivative of gamma m times the velocity, where gamma, of course, depends on v. So this is a non-trivial derivative because the velocity depends on time and is in the gamma factor, and there's a factor of the velocity here. So to derive Newton's second law, we have to take this derivative, and I'll refer you to the attached PDF for the details, but I encourage you to try this at home. You'll just need to use the chain rule a few times. The answer is that relativistically we find that the force is equal to gamma cubed times ma, mass times acceleration, dv dt. So relativistically, we see that this extra gamma cubed is in front of Newton's second law. And of course, gamma goes to 1 as the velocity goes to 0. So at small speeds, this formula just reproduces the normal Newton's second law. But at large speeds, this gamma factor needs to be taken into account. So exactly as we did over here, we'll now set this force equal to the magnitude of the force due to the electric field. So force is the force due to the electric field. And then we'll separate variables and integrate to find the velocity. So this will look like integral gamma cubed m dv equals integral e charge times field dt, where here we're integrating from 0 to t, and here we're integrating from a velocity equals 0 because the electron started at rest to a velocity v, and I put the primes just to differentiate the integration, the variables we're integrating over versus the bounds of the integration. So again, I'll refer you to the attached PDF for the details of doing these integrals. Of course, gamma depends on the velocity, so this is a non-trivial integral to do. Try doing it yourself at home. At the end of the day, we're going to do the integrals, solve for the velocity, exactly like we did over here in the classical case, and then just simplify. And what we'll find is that the velocity as a function of time is the charge times the field times the speed of light over t divided by root mc squared plus this factor that has a t in it. So relativistically, this is what we'd predict the speed of the electron to be after a time t. Now, as before, as t goes to 0, this velocity goes to 0, which is just our initial condition. But in this case, we can see that as t gets very large, if we pulled out a t from the denominator here, then this mc squared would be divided by t, and that term would go to 0 as t got very large. And in fact, as t gets very large, this form of the velocity will approach the speed of light, but never touch it. So, in conclusion, in a finite amount of time, relativistically, we'd actually say the electron can never reach the speed of light in a finite amount of time for any value of the electric field. No matter how large of an electric field, relativistically, we would predict that the electron will never actually reach the speed of light. Let's plug in the numbers for an electric field of 10 to the 7 volts per meter. For electrons accelerated for just 1/10 of a nanosecond, the velocity as predicted by our formula we derived here would be 0.5 0.51c. Whereas after a tenth of a nanosecond, classically, we would predict the electrons to have a velocity of 0.59c. So after just a tenth of a nanosecond, the relativistic and classical predicted velocities are very similar. However, after 2/10 of a nanosecond, relativistically, we would predict a velocity of 0.76c, while classically, we would predict a velocity of 1.17c. So after just 2/10 of a nanosecond, classically, we would have predicted the electron to already be faster than the speed of light. Now, this experiment has been done. Scientists accelerate electrons through large potential differences to very large speeds, and then smash them together to understand subatomic structure. Scientists at Stanford at the Linear Accelerator have done this experiment and shown that the electrons, although they get very, very, very fast, they never quite reach the speed of light.